Okay, so we are in the last chapter of Chris Kranauskis' book. We'll have a few podcasts which lead to ocean's role in climate change. Let's start with this one on CO2 concentrations in parts per million by volume. Typically that means how many million particles there are and how many CO2 molecules are present out of those million molecules. So we started with the pre-industrial level of 278 ppm, which you remember from the first chapter, or I'll show again that this was what we had coming out of the last ice age, with a little bit of an increase due to human activities already by then in terms of agriculture, forest clearing, sometimes abandoning agricultural land, and recovery of the carbon sequestration by the forests and so on. And that data from other sources is combined with Charles Keeling's Mauna Loa time series here starting in the 1950s, which is much more high resolution, showing seasonal cycle of kicking in of the photosynthesis during spring months, which would reduce the planetary CO2, and then arrival of fall where photosynthesis dominated by the northern hemisphere decreases, and then you have an increase in planetary CO2. So we have increased over time. Now by 2021 we are already at 420 ppm, so the increase has been accelerating over time. So obviously we are now reaching 50% above the pre-industrial levels, but also we are accumulating CO2 because CO2 is an inert gas which has a long residence time. Given a reservoir size and the flux in and the flux out, if you divide the reservoir size by the fluxes in equilibrium, you get what is called residence time, or how long on average a substance remains in the reservoir, let's say in the atmosphere, once it's emitted. So that accumulation is much more important because that's what tends to determine the amount of warming, and also that means if we stop emitting right now, we still have the accumulated CO2 that's going to keep warming the climate for a long time, for some centuries. Okay, so if we then jump straight to the countries with the largest cumulative emissions over 1850 to 2021 in billions of tons of CO2 from fossil fuels, cement, land use, and forestry. So the black part here is from fossil fuel, and the green parts are from land use, deforestation, urbanization, agriculture, and other uses. It's generally referred to as AFOLU. Agriculture, forestry, and other land uses. So you can see US dominates this list with cumulative emissions since 1850 of almost 500 billion tons, most of which comes from fossil fuel and a fair bit comes from land. China has caught up now in the second place. Russia, Brazil, Indonesia, whose large emissions come from land use for Brazil and Indonesia, and Germany has afforested, so has a little bit of a negative land use contribution, which means it has taken up carbon dioxide and has a positive output of some 80 billion tons from fossil fuel use. India has both land use and fossil fuel burning, and stands above UK and Japan, which don't have significant contributions from land use, and so on down to Iran here. But you can also include traded CO2, but that makes little difference in terms of the total cumulative emissions. So US share grows by 0.3 percentage points, and China's shrinks by 1.1 percentage points if you count for how much China exports in terms of embedded carbon in the stuff it manufactures and is used elsewhere, and US imports more than it exports in that sense of trade embedded carbon, but that difference is fairly small. Nonetheless, for all countries, you can look at whether they are net importers or exporters, etc. Okay, so annual global CO2 emissions in gigaton CO2. You can see that annual emissions since 1750 up to 1990, and then China started dominating. India has been growing since. So annual emissions since 1990 shown here in the maroon color says that we can see that 1683 gigatons CO2 have been directly emitted from human activities since before the Industrial Revolution, so 1750. 53.6% of these CO2 emissions, or 902 gigatons of CO2, have been released between 1990 and 2020. So if we compare past emissions, this is the big difference, that the rate at which we are increasing atmospheric CO2 is the fastest in a very, very long time. And this is obviously alarming in terms of what it will do to climate change and how we are getting into some no analog states in terms of climate response of the planet. So looking at a longer term, is it very unusual what we have done since Industrial Revolution? So we looked at this ice core record before from Vostok, atmospheric concentration of CO2 since about 800,000 years ago from Antarctic ice core records, direct measurements at Mauna Loa Observatory, and future predictions based on unmitigated fossil fuel emissions, what we will call business as usual scenarios from the previous emissions scenarios and IPCC report released in 2014 called Assessment Report 5. Nonetheless, you can see that when deglaciation happens, as we said, tends to be rapid as glaciers melt, albedo decreases, more energy is absorbed, and more glacier retreat, and so on. So that abrupt change releases about 80 to 100 ppm into the atmosphere, and the slow glaciation, which also increases glaciers, increases albedo, reflects more energy, absorbs less energy, but temperature cools, so gets drier and snowfall rates fall, so the growth of the glacier slows down. So there is a slow growth of glaciers compared to the rather abrupt melt phase. So then similar amounts are taken up, 80 to 100 ppm are taken up. So this sawtooth pattern in the Pleistocene produced these 100,000 year cycles, and we came out of the last glaciation from about 130,000 years ago to 21,000 years or so, and we looked at how that melt happened with hiccups like the Younger Dryas and the Older Dryas, bowling Allerod events, and so on. And we have increased the CO2 fairly rapidly compared to the past, as you can see, and we are going to continue to very high levels not seen for many tens of millions of years. When dinosaurs were wandering around during the Jurassic Cretaceous, we had such levels as we saw before. So is this increase very unprecedented? Well, not just in terms of numbers. So if you look at the previous two glaciations, they also had 80 to 100 ppm increase, but if you look at the current increase, the rate of increase is really rapid. So the three segments of the full CO2 concentrations in ppm record shifted such that the beginning of the CO2 rises associated with the previous two deglaciations and the modern era begin at coordinate 00 here. So they have been shifted to match the beginning of time of each record. This enables direct comparison of both the amount and rates of change associated with these three time periods. The last and next to last deglaciation were taken to start at minus 15,410 and minus 136,900 years respectively. And the modern era is aligned such that the year 1851 is at 0 on the time axis here. So we're starting at slightly different levels for each case, but it doesn't matter if you look at the rates of increase. the amounts were similar for a while, but then we have now shot fast in many ways. So all the released CO2 goes into various reservoirs in the system. So this is the illustration of carbon reservoirs and components of Earth's climate system, including the atmosphere, ocean, cryosphere, and the solid Earth. So here is the solid Earth, which exchanges CO2 with the atmosphere through volcanic activities and other activities that release slowly or fast the magma and the gases from inside. And of course we are taking out fossil fuels and burning them, similar to an external forcing like the volcano. So black arrows here represent anthropogenic carbon dioxide emissions indicated as flux from solid Earth into the atmosphere and subsequent fluxes of anthropogenic CO2 from the atmosphere into terrestrial biosphere, ocean, and so on. So the Earth system has lots of feedbacks internally, as is obvious from these kinds of variabilities where the orbital forcings just provide a trigger to initiate a glaciation or a deglaciation, but then internal ice albedo feedbacks and ocean circulation, thermohaline circulation, and land uptake and so on give you various time scales that are not exactly matching to the external forcing from the orbit or solar activities and so on. Okay, we will use natural isotopes of carbon coming back in the next podcast to understand how we know that in fact the accumulated carbon since the Industrial Revolution is in fact coming from fossil fuels. Turns out that the detective work you can do with the isotopes is very robust, solid, accurate, reproducible, and so on. So there is no hiding the fact that we have emitted all this CO2 since Industrial Revolution. Then the question that is often raised by the merchants of doubt is whether that CO2 increase is in fact causing a warming or not, and even question whether that warming is dangerous or not, or even beneficial as argued by some, and so on. So we'll look at those before we move on to how ocean takes up the CO2 and the related heat or additional energy trapped because of these increases in greenhouse gases that we are causing. Okay.